Welcome to the Chapter 8, Part 2 notes. This is 8.3 and 8.4. For 8.3, we're starting to look at what's called trigonometry. We're just looking at kind of the introduction to trigonometry in this class. Our goals are to learn what they are and to be able to use sine, cosine, and tangent, which are ratios, to determine the side lengths and angle measurements in right triangles. A couple vocabulary words that we need to be able to use. When we're talking about a reference angle, it means the angle that we're referring to, and it's usually marked either by giving the angle letter or with the Greek letter theta. So theta is like an O with a little squiggle in the middle. That's theta. And it's a Greek letter. And Greek letters are often used to describe angles. So if we're referring to an angle, sometimes it's marked with the Greek letter theta. The hypotenuse, as we've talked about before, is the side length that is the opposite of our 90-degree angle. So we're talking about this side length here. And when we use the word opposite, we can use it for non-right angles as well. So for example, if I wanted to find the opposite of a reference angle, then this would be the opposite side. And we'll use O to indicate opposite side. So that's the one that's directly across from the angle, not touching the angle. And adjacent is the side that does touch the angle, but is not the hypotenuse. So if we have a reference angle here, the adjacent side would be the one that is not the hypotenuse that touches that angle. And we'll use a capital A to represent adjacent. So if we're looking at this first example, our triangle here, if we're using angle J as our reference angle, we'll go ahead and mark it here. And I'll use theta to mark this angle. We want to label the hypotenuse, opposite, and adjacent. Well, the hypotenuse always across from the right angle. Opposite does not touch the angle, and adjacent is the non-hypotenuse side touching the angle. Every right triangle will have a hypotenuse, an opposite, and adjacent for both angles. So does it change if I look at angle L? So let's go ahead and redraw our triangle here. K, J, L. If L is our reference angle now, the hypotenuse doesn't change. However, opposite changed and adjacent changed. So opposite and adjacent switch when we switch our angles, our reference angle. So let's practice labeling hypotenuse, opposite, and adjacent. Go ahead and try it, and then we'll go through it together. So here we have a right angle, so that makes the hypotenuse opposite the right angle. If angle G is our reference angle, opposite of that is on the top, and the adjacent is to the left. For number 2, hypotenuse is opposite of the right angle. Angle K is our reference angle, which makes the left side our opposite and the bottom adjacent. For number 3, hypotenuse always across from the right angle. For opposite and adjacent, we need our reference angle, which is R. Opposite is on the right, and adjacent is at the top. Why is it important to be able to recognize those? Well, we have, for the trigonometric functions, a way of setting up these ratios with opposite, hypotenuse, and adjacent. So sine, which is a function, so for example, if I were to say x squared, squaring it is a function. So sine takes in a number and spits out a new number. Sine of angle A, here's angle A, will be opposite, that's A, over the hypotenuse, which is C. Cosine of angle A, so I take angle A, and the output will be adjacent, which is not the hypotenuse, but the other one that's touching A, that's B, over the hypotenuse, which is C. And tangent for angle A gives us opposite, little a, over adjacent, little b. okay? So the way we can remember this that can be helpful is remembering the word SOH CAH TOA. So like I stubbed my toe and it hurt really bad, so I soaked my toe, SOH CAH TOA, okay? And what that stands for is that sine of an angle equals opposite over hypotenuse. Cosine of an angle equals adjacent over hypotenuse. And tangent of an angle equals opposite over adjacent. SOH CAH TOA. All right. Another important thing is for these trigonometric functions, they always have to have an argument. It means it has to have an angle that the function is acting on. And the way I remember that is think about if I have a square root function, right? I can't say the square root without something inside. There has to be something inside of the square root function. The same thing goes for these trig functions. I take the square root of a number. I take sine, cosine, and tangent of an angle. Let's look at some examples. For our first example, we want to find just the trigonometric ratios here. Now, both of these are angle B, so I'm going to mark angle B here as my reference angle. Tangent, TOA, is opposite over adjacent. Opposite is 12, adjacent is 5. So 12 over 5. And maybe it helps to mark on the diagram, this is opposite and this is adjacent. Cosine, so CAH. So cosine is adjacent over hypotenuse. Adjacent is 5 over the hypotenuse. Well, we don't have that length, but we can find it using the Pythagorean theorem. So we can say the hypotenuse squared equals 12 squared plus 5 squared. Taking the square root of both sides, that gives me 144 plus 25, giving me plus or minus the square root of 169, which is 13. Taking just the positive, the hypotenuse must be 13. If you know your Pythagorean triples, 5, 12, 13 is one of them, then you wouldn't have to do the whole Pythagorean process because you can recognize if the legs are 5, 12, then the hypotenuse must be 13. So it is helpful to know those Pythagorean triples. In our next example, find the trigonometric ratios of each right triangle for angle J. So here's my reference angle, hypotenuse, opposite, adjacent. SOH CAH TOA. So this is adjacent over hypotenuse, which is 8 times the square root of 3 divided by 16. That reduces to the square root of 3 over 2. TOA, opposite over adjacent. That's 8 divided by 8 times the square root of 3. I can reduce that to 1 divided by the square root of 3. But we don't want to leave the square root of 3 in the denominator. So we need to rationalize that. So we get the square root of 3 over 3. Okay, those are the first types of problems we could do. Another useful way that we can use trigonometric functions is if we're given one of the functions, we can actually label all of the sides of the triangle for a similar triangle. Now, in this case, because this is an unreduced fraction, it's pretty safe to assume that those are the side lengths. But remember, I could have reduced that fraction to 3/5, and then it would give me a similar triangle, meaning the sine and tangent values would be the same. But just keep in mind that what we're finding now are the side lengths of any similar triangle. So cosine, CAH, is going to be adjacent over hypotenuse. So we look at angle W. This will be hypotenuse, opposite, adjacent. Adjacent over hypotenuse. Adjacent must be 6, hypotenuse must be 10. I don't know the opposite side, but we can use Pythagorean theorem to find it. So we would need to do 10 squared equals 6 squared plus, let me use a different letter, x, so we don't think it's a 0, squared. So that's x equals plus or minus the square root of 10 squared minus 6 squared, which gives us 100 minus 36 is 64, which is 8. So to find sine, sine of angle W equals opposite, that's 8, over hypotenuse is 10, so that's 4/5. And TOA, that tells us tangent of W equals opposite, which is 8, over adjacent, which is 6, giving us 4/3. Again, we're given one function. We want to find the other two for reference angle G. There's hypotenuse, opposite, adjacent, tangent, TOA, opposite and adjacent. Opposite is 8, adjacent is 15. In order to find the hypotenuse, we'll use Pythagorean theorem. H squared equals 8 squared plus 15 squared. H equals plus or minus the square root of 64 plus 225, giving us the square root of 289, which is 17. To find cosine of G, so CAH, so adjacent over hypotenuse, adjacent is 15, hypotenuse is 17, and sine of angle G, so opposite over hypotenuse, 8 over 17, can't reduce. In our next example, we're doing the same thing, but this one is multiple choice. So we have cosine, which is adjacent over hypotenuse of angle A. Here's my reference angle. Hypotenuse is 85. Adjacent is 13. We can find the value of, or the length of MN, but we can also look at our multiple choice options and say all of these numbers are 13, 85, and 84. So this side length must be 84. So use the multiple choice to help you save on the amount of work that you have to do. So we want to find sine and tangent. Sine of A, so opposite is 84 over 85, the hypotenuse. And tangent, TOA, is opposite over adjacent. So looking at this, sine does not have 13, so it can't be that one and that one. It's got to be B or D, so we look at tangent for those. 84 over 13, not 13 over 84, so it must be D. Number 4, we want to find which is equivalent to sine of V. So here's angle V. Here is my adjacent, my hypotenuse, and my opposite. I don't know the value for opposite, but again, I don't need to know the value. I just need to know which one has the same value. So let's call this X. So sine of V, so opposite over hypotenuse is X over 17. Sine of W would be opposite 15 over 17. Not the same, so it can't be A. Cosine of V, CAH, adjacent over hypotenuse, is 15 over 17. That doesn't match. Sine of angle U is opposite. So opposite over hypotenuse, that'd be 17 over 17. Opposite of a right angle is the hypotenuse. That's not it. And so our last option is cosine of W. Cosine of W, which is CAH adjacent over hypotenuse, X over 17. So sine of an angle is equal to cosine of the other angle. Not the right angle, but the other non-right angle. That's actually where the cosine and cosine, they're called cofunctions because they're equal for opposite angles in a right triangle. For our next example, we want to use the fact that we have an angle measurement in order to find a missing side length. So again, we're setting up these ratios and solving for something. So we want to find the value of x rounded to the nearest tenth. So we need to look at, this is our reference angle. This would be opposite, adjacent, hypotenuse. So we want to know which one uses adjacent and hypotenuse. So CAH, so that's going to be a cosine. So the way we want to set this up is cosine of 15 degrees equals adjacent over hypotenuse. But now we're solving for x, so we multiply both sides by 21. X equals 21 times cosine of 15 degrees. Now, when you do this calculation, there's a couple things you have to keep in mind. I'll show you where to find cosine on your calculator. But first, we need to make sure that we're putting in our function in degree mode. So on your calculator, you're going to go into mode. And yours might look a little bit different than mine, but one of the first options should be radian or degree. So if your calculator has the black box around radian or has radian highlighted, you have to go up, put your cursor over degree, hit enter. And then when you click down or up, degree should have the black box around it. Make sure that degree has the black box around it. So now to get out of this, you're going to do second and then quit right next to the second button, and it will take you back to your main screen. And now we can calculate this 21 times, and then if you look above the 8 two buttons, you'll find sine, cosine, and tangent. So we want cosine, and we want cosine of 15. Now, because we put our calculator in degree mode, we don't have to put a degree symbol or anything like that. So 21 times cosine of 15, and it says round to the nearest tenth, so that will be 20.3. We don't have any units, so we'll leave it unitless. For our next example, we want to do something similar. We're going to set up our ratio first. So I have to say this is the angle I'm looking at. Here's the hypotenuse, opposite, and adjacent. So now I want one that uses opposite and adjacent. So the SOH CAH TOA, that's going to be tangent. So we set up tangent of 54 degrees equals opposite, 15, over adjacent is x. Now, one of the nice properties, remember, about proportions is that I can rewrite this as x over 1 equals 15 over tangent of 54 degrees. So essentially what we're doing is we're switching across, not sideways, but at a diagonal, just like cross multiplication. And so we can write this as x equals 15 divided by tangent of 54 degrees. Into the calculator, 15 divided by, this time we want to use tangent of 54. It's still in degree mode, so I don't have to worry about that. Once it's in degree mode, you don't have to change it back. Enter. 10 point, again to the tenths would be 10.9. 10.9. Let's look at a few more examples. On the next example, we want to find the missing sides. There are two missing sides. So if this is my reference angle, opposite, adjacent, hypotenuse, it doesn't really matter which one you find first, but what we want to do is we only want to use the given information as much as possible. So for example, I'll find adjacent first. So this is using opposite and adjacent. We'll say tangent. So tangent of 66 degrees equals opposite over adjacent. Using our little proportion trick again, we'll say that A equals 29 over tangent of 66 degrees. Into the calculator, 29 divided by tangent of 66 degrees, 12.9. But because that's not exact, I don't want to use that in order to find my other side. I still want to use the given information. So I want to use opposite and hypotenuse. So which function will go with opposite and hypotenuse is sine. So we'll say sine of 66 degrees equals 29 over h. Again, using our proportion trick, h equals 29 divided by sine of 66. 29 divided by sine of 66 degrees gives us 31.7. 31.7. Is there another way that we could have used to find that third side? Absolutely. If we have two sides of a right triangle, we can always use Pythagorean theorem. However, if you use the Pythagorean theorem with a rounded number, your answer might be a little bit off from exact. So whenever possible, you want to use only the exact information that you were given. Okay, our last section of examples for this part of the notes, example 3, use the trigonometric ratios to find the angle measurement. So far we've been using them to find sides, but if we use them backwards, we can actually find angles. And how do we use them backwards? Well, if you look at your calculator, above cosine, there's a little cosine with a -1. That means the opposite of cosine, or cosine inverse, as we say. So for these, we will use inverse, which is cosine with a little -1, sine with the little -1, and tangent with the little -1, in order to calculate an angle measurement. So for these ones, we want to find the measurement of angle B. I'll mark that as my reference angle. The side lengths that I have are opposite and adjacent. So just like before, we'll set this up with tangent. Tangent of angle B equals opposite over adjacent. But just like with a square root, if I have, for example, the square root of, we'll just use B, I can't remove the B from the square root. What I have to do is I have to then square it in order to get B, right? So I have to do the opposite function. So in these examples, the opposite function is the tangent, but tangent inverse. And so what we're going to do is we'll do B equals tangent inverse of 14 over 22. So what we're really doing, just like when we take the square root of both sides of the equation, we're taking tangent inverse of both sides of the equation. Tangent and tangent inverse cancel out. So the only way to get the B out of the tangent function, we're like removing it from the tangent function, is to use tangent inverse. So to do this calculation, you do second tangent, which is tangent inverse, of 14 over 22. And make sure that whole thing is in the parentheses inside of tangent. Enter, and we'll still round to one decimal place, is 32.5. B equals 32.5, but this time it's an angle measurement, so we need to put a degree sign. Let's do another example. B is our reference angle. We're given the adjacent and hypotenuse, so that will be cosine. Cosine of B equals adjacent over hypotenuse. To get B out of cosine, we need to cosine inverse it. So think about cosine inverse of this side and cosine inverse of this side. Cosine and cosine inverse cancel out. So we get that B equals cosine inverse of 8 over 19. Into the calculator it goes. Cosine inverse of 8 over 19 is 65.1. 65.1. This is an angle measurement, so we need the degree sign. Okay, our next example, still using B as our reference angle, now we have opposite and hypotenuse, so that will be sine of angle B equals opposite over hypotenuse, 30 over 40. You can go ahead and reduce that if you want. It doesn't hurt not to reduce it, but if it does reduce, it'll just give you smaller numbers to work with. So if we want to get B out of sine, we need to use sine inverse. That gives us B equals sine inverse of 30 over 40. Into the calculator it goes. Sine inverse of 30 over 40 is 48.6. Again, that is an angle measurement, so we need the degree sign. Okay, I'm going to let you go ahead and try number 2 here, this next example, and then we'll go through it together. So for this example, we're given 2 sides. We need to find the third side, but we also need to find the 2 angles. We actually have a lot of different ways that we can approach this. The first thing I would do, since I have 2 sides and I need the other side, I would use Pythagorean theorem. That doesn't mean you can't do some of the methods we were just looking at, but I think Pythagorean theorem is a little bit easier. So I'm going to set this up as hypotenuse squared equals 16 squared plus 20 squared. This is my hypotenuse. And so we get h equals the square root plus or minus 16 squared plus 20 squared. And I'm just going to put that whole thing straight into the calculator. Square root of 16 squared plus 20 squared is 25.6. We choose the positive for a distance, 25.6. Notice how this is not exact, so I want to avoid using it in my future calculations whenever possible. Next, I'll go ahead and find angle A. And the way that we can find this, we only have one other angle, so the only way that we can find this is by using trig. So if I want to use angle A, I want opposite and adjacent. So that's going to be tangent of angle A equals opposite over adjacent. Then angle A is tangent inverse of 16 over 20. So here we go, tangent inverse of 16 over 20 gives us 38.7. 38.7 degrees. 38.7 degrees. For our last angle, again, we could use trigonometry, or because we have 2 angles, we can always use the triangle sum. 180 minus 90 is always going to be 90. So the 2 angles in a right triangle that are not the right angle will always add up to 90. So that means I can kind of take a shortcut, 90 minus 38.7. 90 minus 38.7 gives us 51.3. And if you use trigonometry, you'll get exactly the same answer. 51.3. Notice I put 2 congruence marks here because those 2 angles are not congruent to each other. Okay, let's take a look at our next section of notes. So 8.4, we're talking about specific ways of setting up angles. So this section is going to use a lot of examples of like word problems and real world examples of where we would start measuring angles. So it'll give a little bit of an application of why we're learning all of this. Our objective is to use angles of elevation and depression in order to solve problems. So as a reminder, when we're solving word problems, we have to remember, always read the problem carefully. Read it, reread it, mark on the problem, write down keywords, things like that. Sketch a diagram if ever possible. And remember, because everything is virtual right now, even if the diagram is given, unless you have it printed out, draw the diagram in your notes. So on the Math Excel, etc., draw the diagram in your notes. Okay, and then label everything that you can so that you know what do you have and what do you still need. So in our first example, we're given a picture. A batter hits a ball at an angle of 52 degrees into the air. If the ball reaches a height of 7.6 feet above the pitcher, then what is the distance from the pitcher to the batter? Okay, so now I have a vague idea of what's going on. I'm going to reread the problem and label the diagram as I go. The batter hits the ball at an angle of 52 degrees. I've got it. If the ball reaches a height of 7.6 feet above the pitcher, so here's the pitcher, above the pitcher is 7.6 feet. What is the distance from the pitcher to the batter? So this is what we're looking for. X is the distance from the pitcher to the batter. Okay, well, what do I know that I can use? I have X, I only have one other side of the triangle, can't use the Pythagorean theorem. I have an angle though, so I can use trigonometry. This is my reference angle, and this is opposite and adjacent. So that tells me we want tangent of 52 degrees equals opposite over adjacent. Using our trick with proportions, we can say that X equals 7.6 divided by tangent of 52 degrees into the calculator. The reason I'm showing you all these calculations, even though I don't usually, is so that you can see me pressing the buttons. You can get used to seeing what that will look like. So 76 divided by tangent of 52 degrees. That's what it should look like in your calculator. 59.4. X equals 59.4. Our unit here is in feet. In our next example, we have a 13-foot ladder leaning against a wall. If the angle at the base of the ladder with the ground is 25 degrees, then find the height of the ladder reaching up the wall. So here's my wall. I've got a ladder leaning against it, and now I'm going to reread the problem to label my diagram. 13-foot ladder. 13-foot ladder leans against a wall. The angle the base of the ladder, that's the bottom, makes with the ground is 25 degrees. Find the height of the ladder reaching up the wall. So that's X. The height the ladder reaches up the wall. So how far up the wall is the ladder leaning against? Okay, so again, I have an angle. I have one side length given and one that I need to find. Trigonometry looks like the best way to solve this. Opposite and hypotenuse tells me we need sine of 25 degrees equals X over 13. This is nice. I can just multiply. X equals 13 sine of 25 degrees is 5.5. 5.5 units are feet. The way that we get angles, remember, is by using the inverse. And when we're using the straightforward, just sine, cosine, tangent, we will end up with distances, lengths of sides. So what are these angles of elevation and depression that were mentioned in our objective? Well, an angle of elevation is how far off the ground. So from the horizontal, how far is the angle? The angle of depression does the same thing, but from the sky. So if I'm above, leaning down, or looking down, that's going to be an angle of depression. Now, the nice thing is that they're both measured from horizontal, and therefore these two lines are parallel and cut by a transversal, giving us alternate interior angles. And so the angle of elevation and the angle of depression are congruent. And we will use that several times. So in our first example here, we want to read, label, and solve. The angle of elevation from the base to the top of the slide is about 13 degrees. So from the base to the top of the slide, angle of elevation says we start at the ground. That is 13 degrees. The height of the slide is 13.4 meters. Height is measuring straight up and down, 13.4 meters. Estimate the length of the slide. So if I'm measuring the slide, I would want to measure along the slide, not along the ground, right? So here we have a right triangle with one angle and one side length. It tells me we need trigonometry. And so we're using opposite and hypotenuse that tells me we need sine. So sine of 13 degrees equals 13.4 over x. Use our proportion trick. X equals 13.4 divided by sine of 13 into the calculator. 13.4 divided by sine of 13 gives us 59.6. 59.6, not degrees because this doesn't give us an angle measurement. It's giving us the length of the slide. I should label X is the length of the slide, and that is in meters. In our next example, we're looking at snowboarding down a hill. The angle of depression is 52 degrees. How far does the snowboard go down the mountain? Well, I'm going to redraw this triangle so that I can label it clearly on my diagram. There's too much going on in the picture. It would be hard to read. So we are given from the picture, from the diagram, that the distance, the horizontal distance, is 1,200 meters. Again, in the word problem, she's skiing down a hill or snowboarding down a hill. The angle of depression from the top down is depression, 52 degrees. How far does she snowboard down the mountain? So again, if we're measuring a distance down the mountain, we measure along the mountain. So X is how far does she snowboard down the mountain. I have one side length and an angle that tells me we'll use trigonometry. This is adjacent and hypotenuse. So we will use cosine. Cosine of 52 degrees equals adjacent, 1,200, over hypotenuse, which is X. Using our proportion trick, which is switching these two, X equals 1,200 over cosine of 52. 1,200 divided by cosine of 52 is 1,949.1. 1949.1. Units are in meters. Let's take a look at our last page of examples. For example 3, we're looking at a sonar operator on a cruiser detecting a submarine at a distance of 500 meters and an angle of depression of 37 degrees. How deep is the submarine? So we've got a boat detecting a submarine, something underneath the water. So we're measuring from the water, from sea level down. The angle of depression going down is 37 degrees. The cruiser is 500 meters from the submarine. So from the cruiser to the submarine is 500 meters, giving us a right triangle with one angle and one side length. And we want to find the depth of the submarine. So X is depth of the submarine. And so we have our angle, opposite, and hypotenuse. That tells me sine of 37 equals X over 500. Solving for X, multiply by 500. X equals 500 times sine of 37. I think you've seen me type into the calculator a lot. So this is 300.9 meters. For number 4, Larry the ladybug is standing 14 feet from a tall tree. The angle of depression from the tree to Larry is 43 degrees. Find the height of the tree. So we have a tree. We have a ladybug. From the tree to the ladybug, the angle of depression, remember from the horizontal down, is 43 degrees. The ladybug is 14 feet from the tree. And we want to know the height of the tree. Okay, so my angle is not in my triangle. What can we do? Well, remember we said the angle of depression is congruent to the angle of elevation. These are parallel lines. And so we can also say that this angle here is 43 degrees. Now we have enough information. X is the height of the tree. I'll put it inside so that you can tell it's the height. And so we can say this is my angle, my reference angle, opposite and adjacent tells me we need tangent. Tangent of 43 degrees equals opposite over adjacent, x over 14. Multiply both sides by 14. X equals, into the calculator, 13.1 feet. And lastly, number 5, we're not going to do the step up. Number 5 here, Alex is going skydiving. The plane takes off at an angle of 26 degrees. So that's this angle here is 26 degrees. Maybe I'll draw it again so I can read it clearly. 26 degrees. If Alex free falls vertically to the ground and lands 285 feet from where the plane took off, 285 feet from where the plane took off, at what altitude did Alex jump from the plane? So here's x. We know this is a right triangle with one angle and one side length. We need to find the other side length. Here's my reference angle, opposite and adjacent. So that tells me we want tangent of 26 degrees equals opposite over adjacent. Multiply both sides. X equals, into the calculator, we get 139 feet. Okay, if you feel like you have a good mastery of this, I know I didn't do very many try this, I just feel like these problems are a little bit more complicated. I wanted to walk you through them so that you don't get used to setting them up incorrectly. So if you feel like you have a good understanding of it, go ahead and try the step-up problems. Otherwise, we'll be doing some similar problems in class on the worksheets.